Welcome to part 2 of 10.3. So here we're going to look for tangent to our polar curves. So you're going to have r is going to equal f of theta, which is going to be some function written in terms of theta. So your r cosine theta becomes f of theta cosine theta, and your y being r sine theta becomes f of theta sine theta. So when we find our derivative, we're going to have to get used to doing a lot of product rules here for our derivatives. So dy over dx is dy over d theta. So looking at the y, we're going to have the derivative of r, so dr over d theta, times sine theta, plus r times the derivative of sine theta is cosine theta. Then your dx over d theta, okay, dr, derivative of r, dr with respect to d theta, times cosine theta, minus r times sine theta, because the derivative of cosine theta is a negative sine theta, so that changes the plus to a minus. So this will be our slope. Now, what will probably happen here is we'll just multiply the cosine theta and sine theta into whatever your function is and create simpler terms and take the derivatives of those. But this is just your basic definition here. So that's our slope of the tangent line to the graph of r equals r of theta at r of theta. This is our formula for the parametric form. This is our polar form rule. Now, for observations, I'm going to do these real quick here because in parametric form we already talked about this. dy over d theta is equal to 0, gives us a horizontal tangent as long as the bottom dx over d theta doesn't equal 0. Remember, we did that in parametric form. And vice versa, dx over d theta equals 0. That's the bottom. Gives us a vertical tangent as long as dy over d theta doesn't equal 0. And if they're both equal to 0, that's inconclusive. That's an indeterminate form, so no conclusion. Now, however, when looking for tangent lines at the pole, r equals 0, so dy over dx will equal tangent of theta if dr over d theta doesn't equal 0. So here's an example. Find the slope of the tangent line at theta equals pi over 3 for the curve r equals 1 plus 2 cosine theta. All right, here we go. Let's do our x's. X equals r cosine theta. Substitute in 1 plus 2 cosine theta, and then multiply into cosine theta. So we'll be taking the derivative of this. Now, a little special note here. I'm following what the author has done, and now that I find y, I'll just do this as I'm talking here. What I have found that what really can get confusing when I do my work, watching what the author does, is they put x over y. Let me get that substituted in, multiplied in, simplify 2 sine theta cosine theta. So anytime you see a sine times cosine, be thinking of your double angle identity. Anyhow, getting back to what I was saying. See, what can be confusing is they have the x over the y, and now I'm always, I'm in a hurry, brain's reacting, it's not thinking. I go find the derivative of this first and I put it on the top because it's the first thing I've written down, but that really belongs on the bottom. So what I do, this is what the author's doing, so I'm following the author, but this is so I don't get confused. When I do my polar stuff, I put y first, x second, so then I can go ahead and do my derivative here and here and build my dy over dx right away. So that could be really helpful for you. But again, like I said, I'm following the author's notation here. So now we got to find the derivative of sine theta plus 2 sine of 2 theta. So that's cosine theta plus 2 cosine 2 theta. Remember, that's a chain rule for this double angle right here. Then up here, the derivative of cosine theta is negative sine theta. Again, another chain rule, bring down the 2. That makes it 4 cosine theta times the derivative of cosine theta, negative sine theta, so that's where there's a negative 4 out there. Really can't do any simple, wait a minute, yes I can. There's a cosine times sine right there. That's a double angle identity, so let's factor out a 2 from the 4. So negative 2 sine of 2 theta. All right, so to find my slope, we're now going to substitute in pi over 3 for all the thetas. So pi over 3 is a 60-degree angle, so cosine of pi over 3, that's going to be a half. 2 pi over 3 is going to be a negative 1/2. That puts me over in quadrant 2. Pi over 3 is radical 3 over 2. 2 pi over 3, I'm over in second quadrant, still radical 3 over 2 for your signs because those y's are still up above the x-axis. All right, so 1/2 minus 2 over 2 is going to be negative 1 over 2. Negative radical 3 over 2 minus 2 radical 3 over 2 is minus 3 radical 3 over 2. Negatives become positives. My 2's can cancel. Rationalize that. Let's see, radical 3 over 9. There's my answer. All right, example 9. Follow that lead that we just had phrased. I want you to pause it. I want you to find the derivative and find the slope. And when you have your answer, come back. So everybody hit pause right now. Pause. All right, welcome back. Here's our r cosine theta, r sine theta. Let's plug those in. Do the derivative. Again, remember, when we're done here, this is the bottom. Okay, so product rule. So cosine of 2 theta times negative sine theta, derivative of cosine, plus cosine theta times the derivative of cosine 2 theta will be negative 2 sine 2 theta. So again, cosine 2 theta. Now the derivative of sine theta is cosine theta. Sine theta, copy down that derivative of cosine 2 theta. Not much, again, we can do in terms of simplifying all that because of the fact that your arguments are different inside your sines and cosines. So we're going to throw in our pi over 4. So we have wait a minute, cosine of 2 pi over 4, that's the same as pi over 2. So that's a 0, and this is a 0. Now, you don't have to crunch these out because they're going to give you zeros. I did, but it's not necessary. But here, cosine of pi over 4 and sine of pi over 4 are radical 2 over 2. You'll get the same thing here. Sine of 2 pi over 4, those are both 1s. So times that negative 2. Top and bottom are exactly the same. So our slope of our tangent line at pi equals 4 for theta is 1. Okay, example 10. Here we got a little bit of a goofy looking r. Nothing changes, but what I would probably do is plug this in as 2 times theta to the negative 1 power, so I can use my power rule on my variable theta when I do the derivative. So I'll substitute that in, and now I'm going to get ready for doing, again, the product rule. So let's start out with dx over d theta. Again, remember, if you want to change it to y on the top, x on the bottom, so it matches dy over dx, power to you, because that's what I would prefer to do. But my dx over d theta is cosine theta times the derivative of 2 theta to the negative 1. Bring down the negative 1. That's the negative 2. Minus 1 from the negative 1 makes it negative 2. All right, plus 2 theta to the negative 1 times the derivative of cosine theta, negative sine theta. Product rule here, if we follow the pattern, sine theta, keep the same derivatives from above, that's in red, and then the derivative of sine theta is cosine theta. All right, so this is going in the numerator, this is going in the denominator, and I opted to put my thetas back into the denominators with a positive power, and I realized, holy cow, that's an ugly fraction. Now I could, if I wanted to, plug in my pi for theta, but I'm probably going to have to do some multiplying of some reciprocals to make this easier to work with. So if you wanted to, we could do this right now. Since 2 over theta is a factor of negative 2 over theta squared, this is, if you will, the bigger factor. So let's multiply by the reciprocal of these two ugly fractions, top and bottom. Cancel, cancel, ooh, cancels. Theta, 2's cancel to just a negative theta in front of both. So a negative theta times a negative sign changes that to a positive theta sine theta. Much better looking for when I now plug in my pi's. Sine of pi is 0. Cosine of pi is negative 1. So this is negative 1. That's a 0. So it looks like we're going to get negative pi times negative 1 is pi over a negative 1, which is negative pi. and there's our slope. Example 11, what points on the curve r equals 5 sine theta where the tangent line is horizontal and vertical? We definitely got to put them in our parametric form so we can find dy over d theta, dx over d theta. So r cosine theta, y cosine theta, we'll substitute those in. Oops, sine theta, cosine theta, that's a double angle identity. So think about multiplying by 2, multiplying by a half. So half times 5 is 5 halves. Now I can change that to 5 halves sine 2 theta. And this just becomes 5 sine squared theta. So dy over d theta, let's take the derivative of this. So that's going to be a chain rule. All right, 2 times 5 is 10 sine theta. Then the derivative of sine theta will be cosine theta. All right, so there's your 5 times 2. Oh, no, let's not multiply the 5 and the 2 together because 2 sine theta cosine theta will turn that into a double angle identity. So we'll call that 5 sine 2 theta. Take the derivative up here on the top. So we're going to have derivative outside, cosine 2 theta, then the derivative of the inside of 2 theta is 2, so that should just be 5 cosine 2 theta when the 2's cancel out. All right, so dy over d theta equals 0, so we're going to set 5 sine of 2 theta equal to 0 and solve this. Well, I can divide over the 5, that's gone. So sine of 2 theta equals 0. All right, so 2 theta equals inverse sine of 0. That's either going to be 0 radians, pi radians, 2 pi radians, so on and so forth. So divide the 2 into those answers there. We get 0 pi over 2 pi for our answers. All right, well, we can cross off the 2 pi and this pi because we're just looking, those would end up being the same as our answers. They're going to be repetitive, so 0 and pi over 2, because 0 and 2 pi are going to be the same location. So 0 and pi will give me the same location. So my point, my theta is 0, and if I put 0 in for sine of theta, that's 0, so 0 times 5, so 0, 0 is my 1 point. Now for pi over 2 for theta, so sine of pi over 2 is 1 times 5, that's 5 comma pi over 2. So that's where my 2 points are coming from, r theta. All right, vertical tangent. This we're going to set dx over d theta equals 0, so 5 cosine 2 theta, divide over the 5. Kind of the same process we did over here. Take the inverse cosine of 0. Let's see, that would be, let's see, when am I 0? That's at pi over 2 and 3 pi over 2 and 5 pi, well, 5 pi over 2 is back to pi over 2. So when I divide this by 2, I really don't need this last 2 answers here. Again, I've gone past that one complete revolution. I'll just be hitting the same tangent line that's vertical at those points. So now, when theta is pi over 4, let's go up to r equals pi over 4. Well, pi over 4 is going to give me radical 2 over 2. So my r is 5 radical 2 over 2, comma pi over 4. And 3 pi over 4, let's see, that's going to put me over in quadrant 2. That's still going to be radical 2 over 2. So 5 radical 2 over 2, comma 3 pi over 4. So these are the points. So I have a horizontal tangent at 0, 0, and at 5, comma pi over 2. Vertical tangent, 5 radical 2 over 2, comma pi over 4, 5 radical 2 over 2, comma 3 pi over 4. All right, calculator verification, changing your mode to parametric y equals x sub 1 and y sub 1 sub t. So if I plug this in, just so you can see where they're touching. So here's my horizontal tangents, here's my vertical tangents. So again, what I did is I took my equations right here, my X and my Y, plug them into my parametric format. Make sure you hit zoom 7 to get it into a trig mode. All right. And then I hit zoom 5 to square it up. Zoom 7, it won't be a perfect looking circle. So zoom square, Z squared will square up your window so you see a perfect circle. You can see how my X tick marks are much wider than my Y's. So I can get it to be squared over here. So again, you plot this on your polar graph, and there's the two horizontals, and there's the two verticals. All right, we'll come to 10.4 in just a minute.